Balvigan Bharati with your mentor Abhilash Sathar. We already shown you 3 problems on the subjects that we were taught in the last segment of the fluid dynamics. Now we'll move to the problem number 4 in this context, and the problem number 4 says two equal drops of water are falling through air with a steady velocity v. If the drop coalesces find the new velocity of the drop. So this is we are talking about the velocity when all the drops become in steady velocity. That means they have attained the terminal velocity, not before than that. So two drops of equal size of, let's say, the water drop, they are moving very close to each other, maybe otherwise coalition bit difficult. So then after they are falling together down, after some time they are coalesce form a bigger droplets or the drops, whatever you say. Okay, coalesce means they are being combined, they are being added together to form this. So let's say the radius of there is r and r, this are being radius r. So as these are of equal size and this being combined, and we can assume there is no mass loss. Okay, and those droplets are not changing their densities in any circumstances because that is not mentioned. So we can think their mass or the volume, the mass will come and density will change. So density is not changing, so we can assume that V1 of these two V1, because these are similar, is equal to V2. This is V2, this is V1, this is V1. So 2V1 is equal to V2. So 2V1 is, what is that? 4/3, because these are spherical in shape, because drops, equal drops. So when the water drops coming through the air, it is making a spherical shape due to surface tension and the friction force due to the air and all that. It is making a circular shape. Pi r cube is equal to, for V2 also I will follow the same formula of sphere, but the radius is capital R we have taken. So this pi 4/3 and pi are obsolete. So what else is remaining? 2r small cube capital R cube. So this will be the relation between their radius. Now the velocity, the terminal velocity for this is v. So v will be how much? 2/9. What else? R cube, R square, sorry, rho minus rho divided by eta, and g will be there, sorry, G also is there. So out of this, this is constant, this is constant, because through the same media it is coming. Rho for water is same, media is same. So all three are density, this are same. So only thing is that we can take k into r square. This is the terminal velocity for this, k is a constant. For second case, if I say this is the terminal velocity v2, this is v1, I say the terminal velocity, this is volume or capital V I have taken as volume, this is small v, distinguishing this is velocity, okay, this is volume, don't confuse with that. So second case also, v2 is the volume, terminal velocity of when it is being merged or coalesced. So this is equal to how much? Constant will be same, r square. So now v2 will be, k will be replaced by this one, small v, that is given here. This is, you can read it as small v divided by k, because from this you can replace k. So k by small r square into capital R square. Okay. Now this what I have to do, small capital R by small r is equal to 2 cube. So if I remove cube, that will be the cube root of 2. So square of this is equal to, square of this is equal to 2 to the power 2 by 3. Okay, now this is r by r whole square into small v. So r by r is equal to 2 to the power 2/3 into v. So new velocity v2 is equal to 2 to the power 2/3 by small v, that is given for the earlier drops. Okay, so this will be your answer. Okay, I'll move to next problem, problem number 5. A steel ball of mass m falls in a viscous liquid with terminal velocity v, with terminal velocity v, if the drops, then the speed, balls of mass 8m, then find the speed, sorry, this language I bit have to change, because in question, actual question, the options are given. I am not taking those options, rather I am try to solve it without any option. Okay, so then find the speed of a ball of mass 8 into m in the same liquid, with terminal velocity. Okay, so what is the meaning that is standing here? The steel ball of mass m falls in a viscous liquid with the terminal velocity v. Then find the speed. This speed is the terminal velocity speed. This is asking speed of the ball of mass 8m in the same liquid with terminal velocity. That means when it is attaining the terminal velocity, at that time what is the speed of that mass. So this is also of a similar kind, because the terminal velocity formula, you know, it is some constant into, the only variation is the media is same, balls are same, densities are not changing, so that sigma minus rho part is not changing. This is same, although the mass is changing, density is same. So we is that only difference will come in your r square, isn't it? And speed of ball, the mass is same, mass is different, mass is 8m. So how that mass is coming into picture? The mass for first case, if I say this is mass, it is spherical, that means 4 by 3 pi r cube. If it is having radius, let's say r cube, into this volume into density. Density of the thing is, I am assuming it is sigma. Okay. For the next case, mass will be 4 by 3. Definitely the r will not be r, it will be something higher r, because the mass is different, but rho, the sigma will be same. But what is between this m2 is 8 of m1, 8m it is being said. So if I equalize this, 4 by 3 pi r cube into sigma is equal to 8 of 4 by 3 pi r cube into sigma. So sigma is not taking part, so these all are obsolete. So what is remaining? It is capital R cube is equal to 8 of small r cube. So that means capital R is equal to 2r. This is the relation that is been taken care due to the mass difference. Now, as because Vt for first case, for m, if I say this is small r, this is Vt I am taken, or V1 I am taking, the critical velocity or the terminal velocity. For second case, the terminal velocity I am taking V2. The constant is same, because there nothing is changing, rho and other things are not changing. Then it is only the difference of this much only. Okay, so now you know this relation. You do a V2 by V1, because you don't know the velocity of second case. So V2, let it be on the numerator. V2 by V1 is, if I do the ratio, this will become r by small r, r by small r whole square. Okay, so the V2 is equal to V1. The V1 is given as V, so we will take it V, small v. R by r is equal to r by small r is equal to 2. So square of that is equal to 2 square. So that is equal to 4 of v. So the second velocity will be 4 of the first velocity. Okay. Fine. I will move to the next problem, that is problem number 6. So this is the last problem on this chapter. This is number 6, and this problem is a small sphere of radius r, small r, falls from rest in a viscous liquid, in a viscous liquid. As a result, heat is produced. due to viscous force. The rate of production of heat the rate of production of heat when the sphere attains its terminal velocity is proportionate to what parameter, and correct degree of that. This part is not there in the question because I know the options in this question. Actually the problem is given accordingly to select correct option out of 4 options. The options are given, but I have to eliminate the options by giving an extra part, so that by while calculating you will automatically find the right answer, and there you no need to have options, because options sometimes it confuse yourself. So if you are able to solve the problem, the options automatically will come, so there is no need of having options. So options are needed for those for when you are solving some numericals, and there you need some nearest value and assumptions can be made. But this kind of problem where there is a definite answer will come, you no need to wait for the options. So whether when you will solve you will get the correct answer. So what does that mean actually? Let me understand. A small pair of balls of radius r falls from the rest. So this is a small ball is moving, small ball coming from rest. The initial velocity is 0 as a result of heat production. That means when it is falling, what are the free body diagram? There is a weight, it is automatically acting, it's upthrust, and there is a force that is across the surface of the ball, it is acting, that is the viscous force. And whatever heat is produced, that is produced by the air. It has been said directly, but by way of the concept of this viscous force, the viscous force always act tangentially with the body. Okay, so when the tangential force is acting between two media due to their relative motion, because the ball is moving there, then relatively the fluid through which it is flowing, liquid through it, that will get a frictional resistance due to the fluid, and when it is rubbing each other due to the relative motion, that will definitely cause a heat energy there on the surface of the ball, and that heat also will be generated on the media through which it is moving. But that is not the question here. The question is that the heat energy produced on the ball itself, that has to be calculated, and that how and which parameter it depends, that has to be calculated. Now to get that, the rate of production of heat, that means heat is nothing but energy. Okay, so energy is nothing but work done, and here work is done by the frictional force Fv, and work done means it will get some displacement. Force into displacement is work done. Displacement, if I say, now what it said, rate of production. So rate means per time, energy per time, work done per time. So if I divide with time, I will get force into velocity. So force into velocity will come. Okay, so now when it is force into velocity, that means it is talking about power. So that means power is what? The rate of doing work or energy per time. That is your power. So power here it is, if I do multiply the Fv, the force, into the velocity, I will get power. So this is the ultimate aim for us. So now if it is so, now what is the force acting here? Fv is nothing but what? 6 for spherical body, we following the Stokes law, pi r into v. Okay, now again v, it is attaining the terminal velocity. So the terminal velocity, now if I say this Fv will applicable for any velocity, but for terminal velocity also it will act. So this will be the terminal velocity. Other things will be same, because this is not changing, this is not changing, the other thing. And Vt, it depends on what? 2 by 9, and at the top G, here is eta, sigma minus rho into r square. So now this part, it's not changing, this is same. So we can write, sorry, this part only not changing. So this is something constant into r square Vt. So now if I replace it here, Vt, this is V, okay, so this is Vt. So if I replace it here, in place of Vt, this is k by r square. So I will replace it here. What I will replace? I am just converting this. This also has some constant. So let it be C into Vt. Now Vt is equal to, we have taken k into r square. So this is no, so this is not constant. This part r is can vary with the shape and size. So r, so this I am taking at C. So this along with C, this will be C into r into k into r square. Okay, so now this is ck into r cube. Fine. So Fv I am getting ck into r square. I am keeping it as it is. Fv is equal to ck, where ck are constant, into r cube, isn't it? Now your power is equal to what I find? Fv into v. So then Fv is equal to ck r cube, and again v is again k into r square. So I'll put it k into r square. So all total ck square r to the power 5. So this is also a constant. So now power is equal to how much? If I write it here, power is equal to ck square r to the power 5, sorry, this is constant. So power is proportionate to r to the power 5. So now all these are constants, so power is proportional to r to the power 5. So our answer will be what is the the rate of production of heat, that is the power. This is, we can call rate of production of heat is power is proportionate to that radius of, proportionate to, you can say radius of the ball, it is small sphere, sorry, radius of the sphere, it is one thing. So with which it is varying, parameter is radius of sphere, and in term of fifth order, this power is proportional to the radius of the sphere in fifth order. This will be our answer. Okay, so this is the end of the chapter fluid mechanics, and I will move to a new subject of mathematics from the next episode. So thank you for now, and as I said, kindly don't forget to review and give your comments so that I can myself can improve my teaching skills. Thank you for now.